Okay, physics, we are talking today about linear motion. Linear motion is that motion wherein objects are moving in a what line? What line? I said it bad. Linear motion is when objects are moving in a line. So, and it doesn't matter what the orientation of that line is, whether the line is horizontally forward or laterally changing direction or falling, which is one we're going to talk about a lot, but moving in a straight line. Motion is described mathematically by speed, primarily. Speed, how do we express speed? Yeah, how fast something is. Speed is how fast something is, the rate at which distance is covered. Expressed as distance per unit time. I like to use this V without an arrow over it for speed, and the V with an arrow over it for velocity. So this is a, and we'll talk real quick here about, we'll have a little side note here. This is a scalar quantity. A scalar quantity, meaning this quantity only has scale, no direction. Only magnitude, only greatness, only an amount, no direction. So speed has magnitude but no direction. 65 miles per hour is a speed. 30 meters per second is a speed. 10 feet per minute is a speed. Any distance unit divided by a time unit, will be a speed unit. And it's calculated by distance divided by time, where V is speed, D is distance, and T is time. How do we measure time in the SI? What's the base unit of time in the SI? Seconds. What's the base unit of distance in the SI? Meters. And then speed, if speed is distance divided by time, the unit for speed in the SI should be meters per second. Yeah, because distance is meters, time is seconds. An important thing to know about motion also, in addition to the fact that we can measure it, is that, well, I'm going to write this pretty big, motion, and therefore speed, which is how we measure motion, is relative. How fast are you going right now, Justice?
0 meters per second.
No, the answer is, it's a meaningless question. How fast, because how fast are you going compared to a car on the highway? How fast are you moving compared to a car on the highway? However fast that car is moving, right? We normally, if we look at that utility truck going by, we normally compare the speed of objects to the ground, but that's not like a universal rule. We're always comparing. How fast are you going relative to the center of planet Earth? Really fast, because the Earth is rotating. How fast are you going compared to the sun? Even faster, because the Earth is moving in a huge orbit over the course of a year. How fast are you moving compared to the center of our galaxy, et cetera, et cetera, et cetera? Because motion is relative. So while to me, in my body, I agree with you, you're not moving. But now, woo, it looks like it. You know, if you are a stupid person who doesn't understand how the world works, you could easily trick yourself into thinking that the world is moving when you go like that. Like, oh, how cool, I, the center of the universe, and the world is moving around me, because motion is relative. We always have to relate motion to some other thing. A proper expression of speed or velocity or acceleration would involve a reference point, something else to which we are referring. So motion is relative. The video talked a little bit about instantaneous speed, which is just the speed something is going at that given second. And remember, that's impossibility to calculate algebraically, because an instant, 0 seconds long, we can't divide by 0. So we calculate that using the differential calculus. Another thing we have about motion, another way of measuring motion, which is related, is velocity. Velocity is the vector rate at which distance is covered. So speed was a scalar quantity. Velocity is a vector quantity. Whereas scalars have only magnitude and no direction, vectors have magnitude and direction. So a proper expression of velocity would be 65 miles per hour north, or 30 meters per second down, or 10 feet per minute from east to west. Those would all be velocities. Do you see the difference? It seems like a subtle or even an unimportant difference, but it is an important difference because this has, we can also measure the direction. We use the Cartesian coordinate grid and trigonometry to measure direction. So we can measure both the scale of it using algebra, and we can measure the direction of it using trigonometry, which is something we will talk about when we get to chapter, I believe it's in chapter 3 of your book. It is chapter 3 of your book. So velocity, with a little arrow of it, is equal to displacement over time. Where v with an arrow, sometimes it's called v arrow, is velocity. S is displacement, which is like distance, but in a certain direction. And t is time. Time is measured in seconds again, displacement is measured in meters, velocity then is also measured in meters per second. Is this a problem that both speed and velocity are measured in meters per second? No. The difference is that this will have to have a direction, and speed does not. And you remember, this is a review from physical science, you remember speed and velocity, right? Yeah. Let's talk now about delta V. This is the first of many times we will talk about delta V in this class. Delta V, what's the delta mean? Do you remember? Delta means change in. Delta is change in. You should remember that because delta we use a lot. Delta is change in any quantity that follows delta. So delta hair color is how your hair color has changed over the last year. Delta shoe size is how your shoe size has changed. Delta V is change in velocity. So delta is just change in. Again, V arrow is velocity. What are the ways that velocity can change? Let's list 3. There are only 3.
Direction.
Yep, change in direction. Oops, sorry. Ditto. So change in. What else?
Speed.
Speed. And that's really it. But we can say change in speed up and change in speed down. The 3 ways, you could actually just say change in speed or change in direction, but the 3 ways that an object can accelerate is to speed up, slow down, or change direction. The reason I break this one up into speed up and speed down is because a lot of times people don't realize that when you slow down, that's also an acceleration. At least from the mechanical or the physical point of view, that's also acceleration. There's a button in the car called the accelerator that makes you go faster. And so people think accelerate means only go faster. But accelerate also means change direction or slow down.
You call it deceleration?
You can, yeah. That's not a physics term. People do use the word deceleration, and that is a defined word. People know what you're talking about. That's not a word that has any meaning in physics. We still call it acceleration, but if you wanted to differentiate between them, you could call it that. To put a finer point on it, it's not like if you call speeding up acceleration, you have to call slowing down deceleration. They're both kinds of acceleration. They're both kinds of acceleration. And the way that we calculate acceleration is acceleration a hat, let me make sure this is still showing up. Yeah, it is. Acceleration equals delta v over, sometimes we use delta t, which is change in time. If you just see just t, that just means elapsed time. And I think we already have, except for acceleration, everything else up there. A is acceleration. Now look at this. If change in velocity is measured in meters per second, and time is measured again in seconds, what's our unit going to be?
Second per
meters per second per second, or we call it meters per second squared. That's the standard unit we use for acceleration, is meters per second squared. Starting from meters per second squared, I'm going to erase everything above this, and we're again going to talk about acceleration, but now of a specific kind. We're still talking about linear motion, but again now of a specific kind called free fall. So acceleration is measured in meters per second squared, and we know that it's change in velocity divided by a change in time. And one way that an object can accelerate is under the influence of gravity. Look at that. Did you see it? It's kind of probably hard to tell on video. It might even be hard to tell in real life because it's kind of low to the ground still. But it does get faster as it falls, doesn't it?
Yeah.
And obviously you know that. You can feel it. If you jump off the diving board or whatever, you can feel that you're getting faster and faster. And that's why falling is scary, because if you fall from a very high place, you go super fast, and then by the time you're landing, you're going 180 miles an hour, and then you turn into nothing. You are instantly, you literally eviscerated, where eviscerate means your viscera, your guts, have come out of you. Yes, that is what happens. So in free fall, an object is let's say accelerating, I like that better, is accelerating only under the force of gravity. So in free fall, we are technically doing what? We're technically neglecting or negating air resistance. Technically negating air resistance. So technically, this little boy is not free falling. Why would I? Well, for one thing, because it's the only demonstration I have. We're not going to go to the moon and do this. But why else would I be comfortable calling this free fall? There is air resistance, but because of the shape of this and because of the height of the fall, it's really not going to take effect. Eventually, if you drop this from, say, a water tower, it would probably reach its terminal velocity, where air resistance equals the force of gravity acting on it. But at this height, it is going to continue to accelerate, especially because of the shape and because of its, well, really, even because of its surface that is presented to the air. Air resistance is kind of a complicated equation that we don't really get into, but it has to do with the density of the fluid through which it's falling, because air does vary in density. It has to do with the cross-sectional area of this, and it does have to do with the weight of this object. Be very careful with that, though, and that's where people for thousands of years, the common sense was heavy objects fall faster than light objects. Let me do a very quick demonstration for you to show you that that is not true. Light object, heavy object. Well, it does seem like I just am wrong, right? It does seem like the light object just fell faster, but now check it out. Which one is heavier? Yeah, there may be some variation, but which one? Do you know which one's heavier? I don't. So I'm just going to crumble this one up. We're going to say this one, they have the same mass, we'll say. So which one should fall faster? If it's just heavy objects fall faster, which one should fall faster? No. If the wrong thing, which is that heavy objects fall faster, if that were true, which one should fall faster? They have the exact same mass. But obviously that is not the case. There's clearly something else going on, and that something else is that reality says, the law of gravity says, they both fall the same speed except for air resistance. The difference is not in their mass, and it's not in the density of the air. The difference is the surface area presented to the air. This one suffers more air resistance than the other one. I like that demonstration because a lot of people come into this room as 8th graders or maybe even freshmen thinking that heavy objects fall faster, because it is still ingrained in our common sense that seems like it must be true, because the light objects we have experience with, leaves, feathers, strands of hair, do fall slower than what we think of as heavy objects. But can you imagine the chaos if that were true? Like, you toss a baby in the air and they just kind of float back down, or when you're driving a car off a cliff, it just like instantly 3,000 miles an hour. It would be chaotic. Everything falls at the same rate. Everything falls at the same constant, fill in the blank. Velocity?
Rate.
No. Rate, we said velocity is a vector rate, but it's not. No, they don't always fall at the same speed. Everything falls with the same constant acceleration. And on Earth, that same constant acceleration is abbreviated lowercase g, and it equals exactly, and you have to have this number memorized, 9.8 meters per second squared. And when I say exactly, I don't mean that. It's 9.8, if I have to remember, I think it's 9.8109 maybe. But we're not, 9.8 is good enough for us for this class. 9.8 meters per second squared. G equals, that is the acceleration due to gravity on Earth, acceleration due to gravity on Earth's surface. Why do I have to qualify it so many times? Why do I have to call it on Earth? Why do I have to specify first where it is?
Because Earth has a specific gravity.
Earth has a specific mass which attracts other masses to it, but in a different degree than masses like the moon have. And why on Earth's surface? Because the further away we get from Earth, the less the Earth's gravity affects that object. And so on Earth's surface, it is 9.8 meters per second squared. Really, reasonably, you can use this number anywhere people live. Like even the height of Mount Everest, we would still round it to 9.8 meters per second. It's only once you get hundreds of miles away from the surface that it really starts to change in any appreciable way. The equations that you need for free fall are V equals gt and d equals 1/2 gt squared, where v again is velocity, g again is, which is right there, t again is time, and d again is distance. All these numbers have been expressed at other parts of your notes. So again, v is velocity, g is acceleration due to gravity, t is time, and d is distance. And from there, it's just plug and chug. What's g always? For all of your problems, unless you're specifically told otherwise, g will be yes and yes. It is acceleration due to gravity, and it's 9.8 meters per second squared. You'll be given either a time or a velocity, and then you'll have to calculate the other. You'll be given either a distance or a time and have to calculate the other. Remember that these two equations are derived from calculus. So they have power beyond having to have a time interval to measure like speed does. To manipulate these, this one you should have a pretty easy time with. Just divide by the thing you want to get rid of. For this one, be careful because this squared means we have to do everything else and then take the square root of whatever thing. So we do often manipulate these. Do you have questions about any of this? Questions about free fall? Questions about acceleration in general? Questions about velocity or speed?